Welcome to the module on using a framework for K-12 science education in Montana. This section is about using the framework to describe the impetus of Montana's science standards and the key concepts of this document that guided the development of the next generation science standards. Our goal for this section is for you to be exposed to information about the development of the framework. Some of you may already know a lot about the framework, but we encourage you to listen through this video just in case there's some additional information. And for those of you who don't have a lot of experience with the framework, this video will give you an opportunity to learn more about how it was developed and what the intentions of the framework were. The second goal is to understand the fundamental organization and intent of the framework. And the third goal is to be able to articulate the benefits of using the framework for our alignment work. For example, for instruction, it may be important for us to ensure students have a broader understanding of content, practice, and foundational science content than it is for us to instruct on specific intersections of the three dimensions of science learning in the next generation standards, which are what the performance expectations call for. You may be asking yourself, why the framework? The framework itself provides guidelines for accomplishing the first of two major goals in K-12 science education. The first guideline is educating all students in science and engineering. The second listed guideline for the K-12 science education is providing the foundational knowledge for those who will become scientists, engineers, technologists, and technicians of the future. Why did they include the second goal as a focus of the framework? It is because it is a key issue in understanding the standards and the framework. In general, the framework calls for all students and citizens to have certain foundational science knowledge that everyone should know to be scientifically literate. The framework is designed to help realize a vision for education and the sciences and engineering in which students over multiple years of schooling actively engage in science. Scientific and engineering practices apply cross-cutting concepts to deepen their understanding of core ideas in these fields. In thinking about POW instruction, it's important for our work to circle back to this guiding document to reflect on these key principles of ensuring all students are prepared to enter into the workforce or to be prepared for their post-secondary endeavors. The authors of the framework during the course of their work generated a list of guiding principles that they feel were interwoven into the framework itself. These principles are based on research and theory and provide the foundation for recommendations that the framework makes about how to achieve meaningful science learning. The guiding principles to the framework are drawn from what is known about the nature of learning science, and these principles underlie both the structure and content of the framework, and we'll go through each of these principles separately. Children are born investigators. Students entering kindergarten have very sophisticated ways of thinking about the world based on their experiences with the world around them. An example of this is to think about babies and toddlers. They begin learning about gravity when they drop things from their high chair over and over again, only to have their mom or dad pick them up repeatedly. All kidding aside, from a very early age, children are observing the world around them. They are learning from natural investigations. Younger children may not have deep understanding about why the natural world is the way it is, or extensive experience with it, but they do have complex reasoning. Their ideas about what they see and how they interact with the environment are important principles to understand as we take a look at our jobs as science educators. Focusing on core ideas and practices. By focusing on a limited set of core ideas, students are less likely to experience coverage of multiple disconnected topics. Often, we talk about a mile-wide and an inch-deep curriculum. By focusing on a limited set of core ideas and practices, students are able to experience deep exploration of important content, as well as time for students to develop meaningful understanding, to actually practice science and engineering, and to reflect on their nature. This focus allows for a more coherent view of science education across grades K through 12. Understanding develops over time. The framework uses learning progressions to address the need to develop a thorough understanding of scientific explanations of the world through sustained opportunities to work with the underlying ideas over a period of years. This provides students a kind of map to mastery of the content and helps teachers better conceptualize how to address and present topics at different grade levels so they can build on prior understanding. Through building on science knowledge over time, our instructional support provides an increasingly sophisticated way of student learning that allows for exposure at developmentally appropriate times. Science and engineering require both knowledge and practice. While the knowledge of science is often specific to the individual disciplines of the practices of science, they are not only essential, but shared across disciplines. It's vital that students are receiving exposure to both knowledge and practice. Engineering has a similar situation, as there is a wide range of knowledge required of engineers. However, there's a key set of practices that all engineers engage in while doing their work. Connecting to students' interests and experiences. In order for students to develop a sustained attraction to science, and for them to appreciate the many ways in which it is pertinent to their daily lives, classroom learning experience in science need to connect with their own interests and experiences. In order to support teachers as they build on prior interests, the disciplinary core idea is identified in the framework or derived not only with an eye towards the knowledge that students bring with them, but also towards the kinds of questions that students are likely to pose themselves at different ages. These questions can frame the curriculum and help to communicate relevance to the student. One tool developed by Achieve to support this question-driven model is the storylines from the Next Generation Science Standards. For example, if we look at kindergarten and the NGSS performance expectation, to help students formulate their own questions, consider this. What happens if you push or pull an object harder? Where do animals live, and why do they live there? What is the weather like today, and how is it different from yesterday? We should strive to have meaningful, authentic, and real-world experiences with science that not only prepare students for the world outside of their K-12 public school, but also that engage them in science beyond our school walls. The final one is promoting equity and equity in science education. This principle requires that all students are provided with equitable opportunities to learn science and become engaged in science and engineering practices. Students should have access to quality space, equipment, teachers to support and motivate their learning and engagement, and adequate time to spend on science. In addition to this, it's important to connect to the interests of all students, including those from diverse cultural communities. For Montana, it is particularly important that our science instruction ensures that all public K-12 students are provided with rich, culturally relevant instruction to recognize the American Indian culture. Where appropriate, our formative assessment work will identify where there are cultural connections and significance that helps ensure our science instruction is culturally responsive to distinct and unique heritage of American Indians. Based on the guiding principles of the framework, 3D teaching and learning was developed to broadly outline the knowledge and practices of the sciences and engineering that all students should learn by the end of high school. The three dimensions are the disciplinary core ideas, or the content of science, the science and engineering practices, or the practice of science, and the cross-cutting concept, those principles that underline all of science, like cause and effect. While the framework separates these dimensions into chapters, in order to facilitate student learning, the dimensions must be woven together in standards, curricula, instruction, and assessments. As you select or develop formative assessment and instructional strategies to meet the science standards, it's important to notice which dimensions are actually being assessed. In order to do this, when describing what a teacher does and what the students do to meet the expectations of the standards, ask yourself, how do I know? How do you know they have the knowledge? How do you know they have the skill or practice? How do you know they have the foundational understanding? What features or observable evidence do you look for? Here's an example of these three dimensions intersecting to create the NGSS performance expectations for kindergarten. Let's look at KLS1-1. Use observations to describe patterns of what plants and animals, including humans, need to survive. This shows us an example of the practice 4, which is analyzing and interpreting data, the cross-cutting concept patterns, and the disciplinary core idea LS1C, which is the organization for matter and energy flow in organisms. We will use reference documents like the one shown here to help us wade through and get very familiar with the three dimensions in this course of study. To end this section of the module, we would like to end with this quote. Ultimately, the interactions between teachers and students in individual classrooms are the determining factor in whether students learn science successfully. Thus, teachers are the linchpin in any effort to change K-12 science education. This quote is why I feel like a course like this is so important. If teachers are the linchpin to the success of students, then providing teachers with a solid foundation in the framework and how it relates to all aspects of instruction, including assessment, will help us get off on the right foot.